Hello, my name is Richard Zanibi, and this is the Chi 2021 Interactivity Demo for the MathDeck Formula Editor. This was work done at the Rochester Institute of Technology and the University of Buffalo in the United States. The motivation for this work is to try and make it easier to enter formulas. So for non-experts, it can be very challenging to use LaTeX because of all the commands needed to enter formulas and structures. But even for expert users, sometimes it would be easier to be able to find little subexpressions in large formulas directly in the image and say delete them or move them there, rather than have to do it in a LaTeX string. And editing complex formulas is tricky, so it might be nice to be able to use search to reduce entry effort. So whether through autocompletion as we're entering formulas, or searching for formulas by name like Eisenstein prime, and then getting the LaTeX directly. So three main design goals. We want a flexible combination of LaTeX entry and manipulating rendered formulas. As noted in the last slide, for very simple LaTeX strings, it's still easy for everyone to type certain formulas, so we want to allow that, but we also want the benefit of being able to modify the rendered formula. We also want to reduce complexity by building up from smaller pieces and allow formula information to be discovered, annotated, and saved. So for editing, we have a LaTeX string panel that shows the tech for the formula at all times on the right-hand side. And then the rendered formula that appears on this formula canvas can be manipulated directly through insertion, replacement, and deletion operations. So let's look at an example of inserting a formula in a rendered formula directly. So here's the Pythagorean theorem incomplete, and so we can actually just insert the 2 on the c for c squared directly by clicking on a button and then entering a LaTeX string. We can also replace subexpressions on the canvas. So in this example, we take the Pythagorean theorem again, and we're going to replace a plus b equals c by x plus y equals z. And notice that the exponents aren't selected, but we've edited the selected tech, and the formula is correctly updated on the canvas and this tech panel on the right-hand side. So we can build from smaller pieces. So have multiple formulas in small bits and then put them together using the formula chips you've just seen that can also be downloaded, and canvas tabs that allow multiple formulas to be edited at once. So here's an example of downloading a chip. So once we have our formula here, we can just download it into a JPEG file, which can then be dragged directly back onto the canvas and turned back into a chip. And all the information for the chip is stored in the JPEG. There's no OCR or anything like that needed for this. So using the tabs, we can start combining formulas. So here we have two formulas in our tabs. We convert one of them to a chip, and now we're going to drag that chip over to the tech panel and just add it to the expression directly. And you can see the tech panel and the rendered formula both get updated. So the deck at the bottom of the application contains three views. So one is for these wiki cards that we've seen that have formulas in their names and some hidden descriptions. And then formulas that we've created or created in a separate tab that we can see and access at any time, and we can favorite some of those formulas as well. Then the third view has a symbol palette that contains symbols and expressions, all in chips that we can use as we need. Here's an example of searching wiki cards by formula. So we have a current formula on the canvas we just created. We click on cards, and now you can see that there's a bunch of formulas that have similar structures and symbols that can be seen. And this is expanding a card for the law of cosines to show that we can view more information about the formulas if we want to. We can also search wiki cards by concept name, so these titles in the cards can be searched directly. So we were looking at the Eisenstein triple and deciding to find other things that involve Eisenstein. And so we start typing and interactively filtering the cards based on the titles on the cards. So in conclusion, this has shown our ways of addressing those three main design principles. So we want to be able to have flexible combination of LaTeX and manipulation of the rendered formula. And we did that using structure editing. We wanted to reduce complexity by building up from smaller pieces using chips and tabs. And we wanted to allow formula information to be discovered, annotated, and saved. And so we have these savable and editable formula chips, as well as the cards themselves, though we couldn't show that for time. And we can save things for later use. We wish to acknowledge Abhishek de Mello, who created the card design, and the Sloan Foundation and the NSF for their support. Thank you very much for your time.